blood plasma. So that hemoglobin allows us to carry a tremendous amount more oxygen. Then the question is, well, do we need all that oxygen? That was what was on your mind, right? In 6 minutes we'll talk about it. All right, so the oxygen content of our blood. Without hemoglobin, right, we can carry about 3 milliliters of oxygen per liter of blood. And if we assume a resting cardiac output of 5 liters per minute, that comes out to 15 milliliters of oxygen per minute gets delivered to our tissues. So rough numbers, it's just numbers to work with to sort of demonstrate the idea. Okay, so 15 milliliters of oxygen per minute gets delivered. With hemoglobin, we get the 3 plus 197 milliliters of oxygen per liter of blood for a total of 200. Multiply that by 5, you get 1,000 milliliters of oxygen per minute. That's a bit more oxygen, and a lot more. Well, do we need all that oxygen? Well, we could look at our resting oxygen consumption rate. So this is supposed to be a bigger V with a little dot over it in subscript O2, but I didn't figure out how to type all that in. So V dot O2, this represents your oxygen consumption rate per unit time. So when you're at rest, how much oxygen are you using? About 250 milliliters of oxygen per minute. So yeah, it's a lot less than we're carrying. It's only a quarter of what we're carrying, but it's still a lot more than we can carry without hemoglobin. We're in big trouble without hemoglobin. We need it. Okay? But we've got all this extra oxygen that we're carrying that we're not really using at rest. But when we become active, then that's when we dip into that extra amount of oxygen we're carrying. Yeah?
People who live at like really crazy high elevations, like people like Nepal or something, do they have a higher concentration of hemoglobin in their systems?
So they're going to have more red blood cells, and they're going to have more hemoglobin, so that they can carry
Just more oxygen.
They can carry more oxygen for a given partial pressure of oxygen. But where they're living, so if you're, let's say you live in Nepal, and maybe your ancestry is from Nepal, right? It's not just you that decide to go live, unless you have lots of Nepal genes in you. You're going to have a lot more hemoglobin you carry, but you're living in an environment that doesn't have a lot of oxygen. So it's not like you're getting all this extra oxygen. You're just now able to get the oxygen you need to keep going. Where you or I, that's been hanging out in San Francisco for years and years and years, we show up in Nepal and we're short of breath just walking to the bathroom. Because we don't have all the extra oxygen carrying capacity to grab the few oxygen molecules that are available at that higher altitude. Okay? So if someone that's lived their whole life in Nepal comes and visits us, well, they're not going to be out of breath as fast as we would. So if we go for a run and everything else held the same, they're going to be able to outrun us. Okay. So about 2% or even less than 2% of the oxygen that we carry is all the blood plasma. 98% or more is found in hemoglobin. And that's how we're transferring or transporting enough oxygen to all these tissues to meet the needs. All right, we've got 2 more minutes. So what I want to do here is just start talking a little bit about the saturation of hemoglobin, and then you guys can go ahead and look at it under different conditions. So we can look at how saturated hemoglobin is with oxygen. Remember, each hemoglobin molecule has 4 binding sites for oxygen. If all those binding sites are full of oxygen, that's hemoglobin's fully saturated, right? Or it could be some percent of full saturation. So to figure this out, we look at the number of oxygen molecules bound to hemoglobin divided by the maximum possible, which would be 4 for any individual hemoglobin molecule, and then multiply that by 100 to get a percent saturation. Okay? All right, so in this picture, we can see all of our hemoglobin molecules are almost entirely fully saturated, right? And so, let's imagine there's a dot in there too. This would represent 100% saturation. Hemoglobin molecules are holding as much as they possibly can. Right? Maybe it's 99 point whatever % saturated. If each hemoglobin molecule is only carrying 2 oxygen molecules, what % saturation is it? 50%, right? It's half saturated. All right, so we could sort of apply this to the saturation curves. So this is what we're going to basically carry us through the rest of the lecture. With these saturation curves, we're going to see a lot of these saturation curves under different conditions. But with all of them, you're going to have the partial pressure of oxygen on the horizontal axis. And you're going to have the hemoglobin saturation on the vertical axis, how saturated it is. It can only go up to 100%. It can only hold so much in hemoglobin. These partial pressures of oxygen represent how it varies depending on where you are in the body. Right? At the lungs, it could be up around, say, 100 millimeters of mercury, partial pressure of oxygen. Right? 0 would mean there's no oxygen left in your blood. So notice that the higher the partial pressure of oxygen, the more saturated hemoglobin is with oxygen. Right? There's higher partial pressure, there's more oxygen available, more of it sticks to hemoglobin and fills it up to a point. And then you can see it gets closer and closer to 100% as you get higher and higher here. Okay? Let me just skip ahead. I know it's 6:25, just 1 second. So what we're going to see is under different conditions, we're going to see different curves. And so each curve is going to represent a different condition. Maybe a change in temperature, maybe a change in carbon dioxide's partial pressure or pH. And notice that the curves under different conditions can change. They change shape, they shift. And so we'll see as the partial pressure of oxygen changes, the saturation changes. Or if you were to look at one specific partial pressure of oxygen, you can see under those 3 conditions how the % saturation changes. So under those conditions, think of holding the partial pressure of oxygen constant to see how things shift. Hopefully that will help you when you sort of decipher these different figures. Make sure you watch this part of the lecture. Watch it from the beginning part of oxygen saturations so you get the full description through, and hopefully it makes sense for you. Yeah, question?
What's right first shift, normal, not first shift? What line is that?
So with this figure, the blue line in the middle represents normal, where the purple and the green represents the change in whatever's normal. So maybe it's a pH change. The blood becomes more acidic or less acidic. That curve can shift one way or the other, depending on which way, for instance, the pH shifts. And so a right shift means the whole thing's moving over to the right, or for a given partial pressure of oxygen, you're decreasing your saturation. If it's a left shift, then you would increase saturation for that partial pressure of oxygen, or the whole curve moves to the left. Okay. Anything else for now? All right, you guys. So if you've got a lab tonight, I'll see you over there. Otherwise, see you on Monday. Don't forget to bring a number 2 pencil on Monday.